Welcome to this second video tutorial, which deals with data exploration with AI Studio. We'll start by dragging one of the sample datasets, the iris dataset that we already used in the first video. In this dataset, we have 150 examples. Those examples are also called instances, objects, feature vectors. They are one of the rows, one of the 150 rows. This first column is just the row number of the datasets. We have 4 regular attributes, which are A1, A2, A3, A4, and 2 special attributes. In green is shown the label, is the thing we want to predict, and in blue is shown a unique ID that this version of the iris dataset has. One good screen to start exploring the data is this statistics button over here, which will show you some statistics descriptors of the different features. If they are real numbers, by default, it shows you, or if they are in general numbers, they show you the minimum and maximum value and the average. By clicking on it, you can also see a histogram that you may open to see in more detail using the data visualization features of Altair AI Studio. In the case of discrete data, nominal data, it shows you counting of frequencies. Is telling us that, for example, the least frequent value for this label is Iris virginica and the most frequent is Iris setosa. In this case, the frequency is the same for all of them. But suppose that you have 75 female, 25% male, you will be seeing that here. And it shows over here other possible values. So this screen is a good starting point to get some idea of whether the age of my patients is old or medium or young, or whether I have mostly males, females, and so on. We may also compute the correlation matrix. All the different rapid miner operators, they have an input port. Exa is from a sample, and that's how it calls the data. And most operators, not all, but most operators, they also have an exa output port. If they have an exa output port, that output port is outputting the unmodified original input, in this case, the same iris dataset. Over here has an additional output port, which is the correlation matrix. If we run it, over here we have one of the outputs of the process. That's the first output, just the iris dataset, and the second is the matrix. The matrix is over here, and we can see the different values of correlations, and we can see that, for example, the attribute A1 is not very correlated with A2 and is highly correlated with A3 and A4. And A3 and A4, they are very highly correlated, 0.96. This matrix can also be visualized as a heat map. This is not very useful for a small data set like this one, but later we'll show a larger data set. And in those cases, it makes much easier to identify the high correlations, both positive and negative, in the data set. Once we have explored a little bit the data set, and by the way, when exploring the data set, just going to this screen over here and checking, for example, you can sort the attributes. This is the minimum value for A1, and this is the maximum, just checking that the minimum and maximum age makes sense, or that the values for gender, for example, make sense, and so on. After exploring the data set in a tabular form and computing some statistics, we typically move to some visualization. The histogram can be useful to see the shape of the different distribution. This is the first attribute, which could more or less be normal. But for example, if we plot the third attribute, we see that at most it could be more or less binomial. This could be a normal distribution. This is not a normal distribution. This may be a normal distribution. And we see that there is a gap over here, which is a very clear hint that that feature can by itself distinguish these instances down here and those instances over there. Again, this is an interesting finding because the different machine learning techniques look for boundaries which separate different type of instances in the feature space. And over here, we have a very simple boundary. If A3 is less than or more than 2.5, it's separating those 50. And if I check the sum of all those instances is 50 instances here from the remaining 100 instances over there. Histograms and in general all plots can be colored by different attributes. In this case, it allows me to color by the label, has to be a discrete attribute in the case of the histogram. And if I color by the label, the class, I see that the instances that I have down here on the left, they are all of them iris setosa, and the ones on the right are iris versicolor and iris virginica. Over here, there seems to be a little bit overlap, but I don't really see very clearly how much overlap. As a matter of fact, there may be some green down there. If, for example, if I plot the histogram for some other attribute which has more overlap among the different species, it's quite unclear from this plot how much overlap there is. It's much useful to plot these histograms using transparency. If you go here to plot style and you select the different colors, for example, the blue, and you move this slider transparency towards more or less the middle, the blue will turn into transparent. This case not really that useful because all the other colors were on top of the blue, but I'll do the same for the green and for the orange. And in the case I had more possible values for the class, I will keep doing that. And now I can see behind the different bars of the histogram, and I can see that indeed there is a little bit of blue down there and more blue over here, and there is green over here, but there is also green behind the orange over there. So there is a lot of overlap in the values for this attribute for the three ID species. However, in the case of A3, this species is completely separated, and over here there are a little bit overlap, but not that much overlap. So this attribute is going to be more useful to distinguish between the different ID species than, for example, the attribute A1. It's a good practice to explore all the attributes. This attribute, all the classes are also quite mixed. In the case of A4, there is also separation of one of the classes versus the others, and there is not too much overlap over here. Maybe the separation was a little bit more clear in the A3 attribute, but over here this attribute clearly is more useful to separate the classes than, for example, the first or the second attribute. You can change if you want, and sometimes it's useful, the number of beings. So for example, instead of 10 beings, I may plot this with 5 beings, which is more coarse, and now it's showing a little bit of overlap over here because the beings are much wider, or 20 beings, where I can see more clearly the degree of separation between the different species. After the histogram, we typically move to scatter plots, and you may start by just plotting the scatter matrix, which is a matrix with all the different scatter plots. I'm going to select all the attributes, and they're going to be in order for the first to the last one. AI Studio only allows you to plot 10 different features in the scatter plot matrix. You can change the size of the different plots over here, depending on the size of your screen. And again, you can use color. You could use some feature to color, or you can use, which is the most common option, the class to color. So here we see the 3 different species, and for example down there we see that in the scatter plot of A3 versus A4, down here I have all the iris setosa, and it's well separated from versicolor and virginica, and over there is a little bit of overlap. You can also use the plot style options. As a matter of fact, it's still using the options that we select before for a little bit of transparency for the different colors, which can be handy to see how many dots I have in different regions. Let's, for example, plot in more detail the scatter plot of A3 versus A4. You can see that some of these green dots are darker than those other green dots over there. The reason why is that in reality there are several instances over there. The same goes here. This blue dot is darker than that other blue dot over there. The reason why this is happening is because the different measurements in the iris datasets, they have a resolution of 0.1 millimeter, and there are multiple flowers which have exactly the same length of width for one of the sepals and petals. So this dot over here, it may be 3, 4, 2, or 15 different flowers. If you actually counted these dots, you will see much less than 150 instances. If you were plotting non-metric data, if you were plotting, for example, gender information, there are only two possible regions of the projection of the feature space where gender may fall, male, female. And that will mean that you will have, typically, if you are, for example, plotting education level versus gender, you will have very few dots in the feature space containing all your data. We'll see an example in a moment, but besides using transparency, which makes clear that, for example, there are more instances in that green dot than in the green dot over here, you can add jitter to the plot. And jitter are small random values which get added to the instances. If you see now those green dots, they are more or less have the same color. Over here we still get some dark blue dots. But if I keep adding the jitter, which is a small x and y random value, the dots move around a little bit, and that allows me to see how much data do I really have behind a single point. I'm going to grab the Titanic dataset to make more clear the value of adding jitter. This is the Titanic dataset. One of the interesting things to notice about the Titanic dataset is that we have missing data. Over there we have a question mark. In the iris dataset we don't have any missing data. Over here you can tell it to show just missing attribute data. So these are the instances which have some piece of data missing. And there are a lot of instances over here. So many instances, they have some piece of data missing over here. Again, if we go to the statistics screen, for example, we can see very fast that the overall population or the overall passengers of the Titanic were prevalently male. I have 840 males versus 460 females, so I had more males. I can also see the age distribution. It was mostly young people between 20 and 30 years. I don't have a lot of elderly. I do have some children, though. I can see, for example, that that the survive 809 people did not survive, 500 survived, so most people actually died. And I can see that, as one will be expecting, most people were traveling in third class. Second class actually had less passengers than the first class. This is a little bit curious, but I guess that was the case. The thing I want to show you here, it was a scatter plot of survive, for example, which has two possible values, yes and no, versus gender. There are only 4 possible regions of the feature space where a dot may fall in this two-dimensional projection of this dataset. Either you are a woman and did not survive, or a woman and survive, a men and do not survive, a men and survive. And in this plot, I have no clue of how many men and women survive or died. If I add jitter, you can see how those clouds are increasing in size. And if I add a large amount of jitter, it'll be very clear that, for example, most women, most female are down here, and most male are up there. So this is one of the usefulness of the jitter. Let's go back to the iris dataset. Besides scatter plots, other of the visualizations we cover in the course are parallel plots, which are here, parallel coordinates. I need to choose the different axes, so I'll do it in order. This parallel plot is colored by class, and we can see, for example, how between the A1 and A2 attribute over here, there is no order. Lines tend to cross each other, so there is no correlation between A1 and A3. And for example, there is correlation between A3 and A4. Lines here are much more order. Over here, in the case of the Vesicolor and Virginica classes, especially for Virginica, there is less order, there is more line crossing each other. However, for the Setosa and also for the Vesicolor, there tends to be a little bit more order. If we see those lines over here, those lines over there, they correspond with this scatter plot. I'll remove the jitter, so you see the original scatter plot. There is no clear correlation here. If I go to the correlation matrix, this corresponds to the minus 0.1 correlation, which pretty much means there is no correlation among those pieces of data. That's a very low value for the correlation. If I, however, go back to the scatter plots and I represent the scatter plot of A3 versus A4, I see a very clear, strong correlation. All the data tends to be around the diagonal. This corresponds in the parallel plot. With the lines being ordered and not tending to cross each other. You can see them here. You can see how the lines tend to be ordered when we compare it with here. Low correlation, high correlation. Again, if we go to the correlation matrix, it was the correlation between, yes, as a matrix, between A3 and A4, and that's a quite high correlation, 0.96. Now, let's grab another data set with a lot of data, because both of these are quite simple data sets. It's going to be a Weka data set. I'm going to need an operator, the read ARFF operator, to import it. I need to tell it where my dataset file it is within data, classification, and the Wisconsin database breast cancer dataset. This is the one we're going to open. If we run it, we'll see that we have 569 examples, 569 instances. There are 31 attributes. It says that there are no special attributes. The class is this column over here. It did not recognize it as the class. I could use the set role operator to specify that the attribute whose name is class is not a regular attribute, but is the label of the class. If I run the process again, now that has one attribute, one special attribute, the class, and 30 regular attributes. And for example, if I go to statistics, I can very easily see that there are two possible values for the class: malign tumor, benign tumor. Those are the possible two values for the class. I can also see the range. For example, the first attribute has a minimum value of 6.9, a maximum of 28, and an average of 14. And A4 has a minimum value of 143, a maximum of 2000, very different ranges. If I plot a scatter plot matrix, I can at most choose 10 different variables. I'm going to choose just the first 6. The tool AI Studio does not allow you to choose more than 10 variables. Over here, we can see that in this dataset, some of the attributes, for example, the first one and the second one, have very small correlation. However, I'm going to decrease the chart size to see all of them. However, some of them, they have very strong correlation. This is a really strong correlation. And some of them, such as this one over here, A3 and A4, they do have a correlation which seems to be non-linear. Others down here, they have a little bit correlation, or that one over there. They are not as shapeless clouds as, for example, this scatter plot over here, but they don't have such a strong correlation. These correlations over here are a hint of nonlinear behavior. I could see in more detail, for example, the scatter plot of A3, I think was one of the features, would have a nonlinear correlation with A4. It's not very clear, but there is a hint over here of a curve. This is not a perfect straight line, okay? So some of the features over here, they have nonlinear behavior. Over here, there is a very strong linear correlation with A1 and A3. However, A2 and A3 have no correlation pretty much. I could color by the class and, for example, see that the malign tumors tend to fall up there and the benigns down here. And for example, if we check the two attributes, we have the nonlinear correlations. Over here, there seems to be mostly benign, and for high values, mostly malign tumors. If in this case I compute the correlation matrix, I can indeed check that there is a lot of high values. There's a lot of correlations in the datasets. There are also small values. A1 and A2 did not have a strong correlation. However, A1 and A3, they have a 0.998 correlation, a very strong correlation. I can visualize this matrix as a heat map. In this case, is handy. For example, I can look for the negative correlations, not very strong. I have no dark blues here, so most correlations are positive, and the few negatives are not very strong, but I do have a lot of dark reds, which are very high values of correlations between the attributes. This is going to be useful because in this dataset, I have less than 600 instances and 30 attributes. 30 square is 900. Therefore, the number of dimensions of the feature space, 30 raised to the square, is not much less than the number of instances. We are in trouble over there, but given that this dataset is highly correlated, there is a transformation principal component analysis that will be covered later in the video that can be useful. There are more visualizations that we have available from RapidMiner. Ones of the others that we cover in the course are box plots. For example, this is a box plot for the first attribute for the 3 different species of iris flower. There will be a box plot for the second attribute. third attribute, and so on. Over here, there seems to be no potential outliers. There seems to be some distributions such as this one over here, where the middle bar is not in the middle. So average and median are very different from each other, which is giving us a clue that for this species, the fourth attribute follows a very clearly non-normal distribution. Again, this can be assessed by checking the histograms. If we plot some scatter plots, well, no data is still showing over here as an outlier. By the way, when this happens, when we have one attribute which has such a very different range than the other, that's hindering the visualization of the other box plots. So just remove that one. And now we can actually see a little bit about these ones over here. I still cannot see anything about those ones over there. So if I wanted to see what's going on with the remaining box plots, I need to remove these ones. And now I can see the remaining ones. Not really sure there is an attribute here which has a clear outlier. I'm just going to randomly add a couple more attributes. But if we had an outlier, nothing is showing here. I'll remove 23. Potential outliers, the data which falls outside the whiskers, are represented as dots. There is no value over here, which looks like an outlier, but if we had a dot outside the whiskers, that would be potential outliers. There is other type of visualization. For example, you have a 3D scatter plot that can sometimes be useful. You have bar plots and so on. But in general, my advice, as I already mentioned in the theoretical part of the course, is start by the histogram, move to the scatter plot matrix, and then it depends on what you see. You may want to check the other plots. Before actually plotting the data, start by computing the descriptive statistics and probably the correlation matrix. With this, we are done. If you want to save the process, remember that you can go here, click on Save Process, and you may do it in your local repository, or if you have created another repository, you can use that one, and you can save it as, for example, Data Exploration. I'll see you in the next video.